So today we're going to look at one different way to calculate the enthalpy change for a reaction. We already looked at calorimetry. So today we're going to look at Hess's law. And Hess's law is a great way to find the enthalpy change for a reaction. Now, Hess's law is a theoretical method, right? And so it requires some prior knowledge of different types of chemical reactions, but we'll take a look at that. So what is Hess's law, right? The book, your textbook actually defines it, and going from a particular set of reactants to a particular set of products. The enthalpy change, or delta H, is the same whether the reaction takes place in one step or a series of steps. So if we think about it, looking at the energy diagram here, right, here's our particular set of reactants, here's our product, right? And it doesn't really matter if we go in one, oh, that's a bad color. If we go in a single step from here, activation energy coming back here, right? If we look at it, it really doesn't matter because the energy change is the same, right? So delta H would be negative in that case. Now, even if we kind of did this and we had, this would be like if we had a single step, right? So thinking back to kinetics, we have a single step reaction. Now let's say we had a multi-step reaction. So here the red line would be our multi-step, right? We have step 1, we have step 2, we have step 3. So in this case here, actually we have step 4. I missed that one. So in this case, we actually have 4 steps, right? And what we're going to see with Hess's law is Hess's law says if we kind of take into consideration the energy changes of all these different reactions, right? Reaction 1, reaction 2, reaction 3, and reaction 4, and we kind of added those all up, we're going to end up with the energy change of the overall because we're still going from point A to point B in our reaction. So that's what we're going to make use of when we do Hess's law. So let's see this in action, right? So for Hess's law, we're going to need a chemical reaction where we don't really know what delta H is. So we're looking for delta H. We don't know what the delta H for this particular chemical reaction would be. But what we do know is we have a series of chemical reactions where we do know the delta H for because these are pretty common, right? We have the combustion of what is propane, right? And so the combustion of propane, we know that that produces a certain amount of energy. We have the synthesis of water, and we know that that produces a very specific amount of energy. And then we have the synthesis of carbon dioxide from its elements. And again, we know what that thing is. And so how can we use these known quantities to come up with this delta H for this overall reaction that we don't know? And we're going to use Hess's law. So how do we manipulate these? So we're going to have to do a little bit of manipulation because if we add these just up like this, right? If I were to take these equations and kind of add them together like we did when we did our reaction mechanisms, when I add them up, I'm not going to get this overall. And so the goal is when we add these up, these 3 steps, step 1, step 1, 2, and 3, when we add those all up and we cancel things out that we can cancel that appear on opposite sides, we get the overall reaction. So let's talk about how we know and how we can do that. Well, when I look at manipulating reactions, basically I'm looking for things that are unique. So in this case here, I see that reaction 1 is the only source of C3H8 with all 3. And if this reaction 1, we see it's on the product side here, but it's in the reactant side right here. And so since it's on the reactant side here, but it's in the product of the reaction that we want to, we're going to have to flip that first equation, right? And so we're just going to flip it to get the reverse. So 3CO2 plus 4H2O gives me C3H8 plus 5O2. So I just flipped that reaction. The reason why I wanted to flip it, now my CH3 or C3H8, are on the same side of the arrow. That's where I want it. I want it to be a product. I need it to be a product. Now, when I do that, the question becomes, well, what do I do with delta H, right? Well, we know that basically delta H is the same magnitude but opposite sign when you flip the reaction for the reverse process. So in this case, I just flipped this over. So instead of being a negative 2044, I'm going to need a positive 2044. All right, so I just flipped that reaction. I just manipulated this, and I manipulated delta H accordingly. All right, so let's look at the second reaction here. And so if I'm looking at the second reaction, I'm saying, okay, well, I have H2 and C left, and oh, lo and behold, right, here's H2. This reaction number 2, is the only source of H2. And since it's the only source of H2 and I need 4 H2s in the overall, I need to manipulate this reaction here so I can get 4. And the easiest way to do that is to multiply this reaction by 2. So if I would multiply that reaction by 2, right, I'm going to do 4H2 plus 2O2 gives me 4H2O. But what I do to this, I have to do to delta H. So I have to multiply delta H by 2 as well. So delta H is going to be equal to negative 968 kilojoules. Okay. All right, so manipulated the first two. Now let's look at the last one. The last one, right? Ooh, we have C left up there that we haven't accounted for. Hey, this is the only source of C. And so for this last one, you guessed it, we're going to have to multiply by 3 in order for us to have that. And so we're going to take this and multiply this by 3. And so if we get 3C plus 3O2 goes to 3CO2. And what we do to that, we have to do to delta H. And so delta H becomes a negative 11,085, right? And, oh, is that? I think I put that in. Let me double check something. There should be a decimal point there. Sorry, guys, there's a decimal point. That's what I thought. Okay, so there you have that, right? So now, all right, the question is, well, now what, Lambert? What do we do now? Well, let's look at and focus only on the manipulated ones, right? So we just manipulated these, so let's get rid of them so they don't get in our way. All right, and so now we're going to take the ones that we have left, and now we're going to add these all together. And I'm going to do that in red so we don't get confused. And so now, but again, before we add, let's cancel things out that appear on opposite sides of the arrow. So if I look here, I have 3 CO2s here, and in the third equation, I have 3 CO2s, so I can cancel those out. What else can I cancel out? I have 4H2 here, and in the second equation, I have 4H2Os there. I can cancel those out. Here I have 2 O2s. I have 5 there, so I can cancel that out. And I cancel that, it will leave me with 3. And then down here, I still have another 3, so I can cancel, and then I can cancel out the rest of those. So now I've canceled out everything that I wanted to, and so that's going to leave me with my 3C plus 4H2 going to 3C3H8. And if I did this correctly, this should match what we are trying to find. And we see that it does. So I manipulated that correctly. So now, basically what that means is now I get to just add up my delta H. So delta H in this case, I add those up, it's going to be equal to a negative 104.5. So if I'm looking for what delta H is for that reaction, it would be a negative 104.5. So there you have that. Now, the thing about this, in this particular case, we were just we multiply through, but sometimes you may have to divide through. Okay, and so for instance, I'm going to go back here, and even now that we're complete, and let's say I have my 2H2 plus O2 going to 2H2O, where delta H is equal to negative 484. And let's say for some reason I would have to take this and I would have to divide this by 2, right? And so when I divide that by 2, I'd have H2 plus 1/2 O2 goes to H2O. And that may seem weird to have 1/2, but remember, if we think about it in terms of moles, it'd be 1 mole of H2 reacts with 1/2 mole of O2 to produce 1 mole of H2O. So I can very much have 1/2 mole of something. But if I divide that by 2, again, my delta H, I'm also going to have to divide by 2. And so the delta H for that would be a negative 242 kilojoules. Okay, so just remember, we can multiply, but we can also divide. All right, so make sure you're working the practice problems from the assessments for today, and reach out if you need me. All right, guys. Peace, love, happiness. Thanks for playing.